Okay, I think we can start. Before we begin, are there any questions?
Can I say something?
Sure.
Last week you gave us some homework.
Mm-hmm.
During this week, I think all of us solved the questions, but the questions were so hard and we suffered a lot to
Okay. Well.
solve the questions, and it is really interesting that our background, for example, 70% of our background is engineering, not physics. And can you please care about the details and concepts of the
Okay.
because our knowledge, I think this is an opinion of most of us, but maybe they are shy to
Okay.
tell.
Well, I mentioned this earlier, but probably you guys forgot. But the purpose of the homework was actually not for you to suffer, but for you to really study and learn out of the class, because this course is really about mesoscopic physics and materials and so on. So the idea here is not to teach quantum mechanics. You should learn quantum mechanics elsewhere. It can be 517, it can be from homework, it can be from your previous background. So the first 3 weeks or 4 weeks now, the idea is to show you the concepts that you at least have to have a basic understanding of, and then we'll use these concepts in our later topics. So the idea here is that put you through that struggle of solving those questions so that you can learn certain things from that struggle. So, of course, we can always discuss. I mean, my door is open, my windows are transparent. So you can always come by and ask questions to me, and we can discuss the questions. That's one way to learn things.
But is the question an exam of questions?
No. Exams are not going to be like this. Again, this is not an undergraduate course. Our sole purpose here is to learn new things. And since you are graduate level students, I have little doubt about your ambition to learn new things. Okay, this is not an undergraduate level where I try to rank people and measure how much they learn and so on. The more you learn, the more you'll benefit, because this is one way or another is related to your research or will be related to your research. So the exams are going to be much more simpler. They're going to be more like quizzes. The questions will be more conceptual rather than solving things. But the homeworks are going to be difficult, because the particular focus there is you to learn new things. Go out to do research, read books, and learn new things. So it's part of this whole learning process. I hope it makes more sense now, but the exams are not going to be anywhere near like homeworks. But they're going to be difficult conceptually. It is going to, of course, I have to measure something so that I can, that's the unfortunate side of giving a course. I mean, somehow I need a metric to measure the performances of the students. But again, there's not much to worry about, because typically for graduate level courses, especially for an advanced graduate level course like this, the average is set so high that no one fails, no one gets a low score. So don't worry about grades. Try to focus on what you can learn from this course. Okay, that's much more important. Well, do you have any other questions regarding the homework itself, the homework questions? Yes? Oh yeah, I'll upload the solutions once you turn in the homeworks. Okay. And you'll see it's not too difficult, actually. If you really read a few books or Google the some of the questions, you can easily find the solutions and see how to solve the relevant equations. Okay. Right, so...
How do you read that fifth question? That was a puzzling question.
I don't remember what the fifth...
Probability. Like it has 4 cases.
Oh, yeah. Well, it's actually a simple quantum mechanical question. Now, the idea, it really shows how strange the quantum mechanics is. Now, you have an observable, A, which can have 2 states, okay, with 2, we call them eigenvalues, or values simply, that are 2 states that it corresponds to. And then there is another observable, B, with 2 observables and 2 outcomes. And these observables are related to each other. So you cannot measure them simultaneously with infinite precision, which means they obey Heisenberg's uncertainty principle. So the rest is just understanding this basic thing. So this guy is related to these 2 states. So if you perform a measurement, there's a certain probability of getting A1 and getting A2, and there's a certain probability of getting B1 and B2. And once you get, for instance, after a measurement, A1, then if you perform a measurement B on this state, then the probabilities will be these 2. So depending on your prior knowledge about the states, the probabilities of the outcomes change. And this is a very interesting thing that you can only observe in quantum mechanics. I think it's an illustration of the point. And there are systems that you can study like this, like spin systems, and we will see some examples of them. We'll discuss the solutions later. So, last time we were dealing with semiconductors. And if you remember, the idea was this. We have this dispersion relation where we had the conduction band and the valence band, and then there was an energy gap. Okay, and depending on the extremum points of the conduction band and valence band, their position in the K space, we classified them as indirect or direct band gap semiconductors. And then this whole discussion evolved into focusing on a narrow region in the near the extremum points of the conduction band and the valence band. And now we are mostly interested in the behavior of electrons near these regions. So now I'll draw simplified band diagrams where typically we are focused on a very narrow point within this K space, because as we have discussed, most of the electrons' motion indeed take place within the vicinity of this extremum points. Now, one thing we did was we had these electrons. So this was my Fermi level, okay, and in the valence band, the electrons were the valence band was completely filled, and then we looked at what happens when the temperature is greater than 0, and what we have seen there was, because of the probability distribution, okay, so this is my baseline, some of the electrons will be here, and the electrons that left here will leave holes behind. Okay? And these holes, as much as these electrons contribute to the electrical properties of the materials. So we defined, for instance, the total mobility as electron density, electron charge, mobility of the electrons plus density of the holes. We realize that they carry the same but opposite sign, charge, mobility of the holes. So the total mobility of the system is defined by both the electrons and the holes. And then we have seen that these guys can be different from each other because now the interactions that electrons and holes are different as the curvature of this conduction band and valence band might be different. So it vastly affects the mobilities because we introduce something called effective mass. And the idea here was we collect all the, let me say, forces acting on electrons and holes into a term. So it gives us a modified mass. And that modified mass changes the mobilities, thus the electrical properties. Now, the next thing we would like to do is this. If you look at the system, it's somewhat boring. I mean, okay, I have to increase the temperature so that I'll have electrons and holes here, but there's not much I can do with such a system. So the question is, what happens if I add impurities into the system? Namely, if I add dopants. So what do I mean by doping? Let's say I have a crystal like this. I'm just making this up. And especially for a semiconductor like silicon, you'll see that these atoms are completely satisfied because each silicon atom makes bond with 4 of its neighbors, okay? And it's perfectly satisfied under this configuration. Now the question is, what happens if I introduce something else other than silicon into this lattice? It may have, for instance, 1 extra electron or 1 less electron compared to silicon, which means that extra electron, for instance, now one example is phosphorus for this, one example is boron for this one. So this has 3 valence electrons, this has 5 valence electrons, compared to silicon that has 4 valence electrons that can contribute to bonding. Now, in this case, there will be 1 extra electron in the system. So you will use these for bonding. But now, these are neutral in terms of the charge, but there will be a positive ion core that is not screened. This makes sense, right? Now, in the case of silicon, consider a case where these electrons are completely used in binding. Since the electrons are in the vicinity of the ion core, it will screen the charges. If you add up the protons and electrons, the number will be equal. But in this case, now I have 4 electrons that are used for binding, and this 1 extra electron will not be in the binding. So what I'm going to end up with a positively charged ion core and a negatively charged electron in the vicinity of that positively charged ion core. Does that resemble something to you? This configuration, a positively charged particle with an electron. What's that? So we have a positively charged particle here that's fixed in space, and then electron that can orbit around. So it's like a very primitive hydrogen atom. So it's like a hydrogen atom. Likewise, we can do the same thing for boron, where you have now one missing electron. So you need to add an electron into the system so that it can make bonds with the 4 neighboring silicon atoms. In this case, you'll have a negatively charged ion core, because now you got electron from somewhere else that's used in binding, and there will be an absence of electron in the vicinity. So it's like an inverted hydrogen atom. You have a negatively charged particle fixed at the center and hole that orbits around that particle. Okay? Now, what is the purpose of doping? Let's say I started introducing more and more electrons into this system. What will happen? Now, this is my intrinsic case, and now I started introducing more and more electrons. And these electrons are mobile electrons where they can live in the conduction band, and they're coming from these impurity atoms. So I don't have to take any electrons from the valence band and take them to the conduction band. So the net effect of this doping will be an increase of the Fermi level. So the Fermi level in the case of electron-rich doping, which is called N-type doping, will shift the Fermi level closer to the conduction band. So now, another way to look at this is that since my Fermi level has shifted up, the distribution, even at finite temperatures, will be shifted. My 50% probability will be much higher. So this shows me in a way that I don't have to transfer any electrons from the valence band to the conduction band. The opposite case is this. I'll have holes abundant, so there will be lots of holes in the conduction band, and of course, lots of holes in the valence band, and no electrons in the conduction band, because now I'm depleting already available electrons within the conduction band. So the Fermi level will be lowered towards the valence band. So this is hole-rich doping, and it's called P-type doping. Okay. This is an extremely common practice in semiconductor industry, and this is why we can have all the electronics we have around us, because without doping, it wouldn't be possible to make functional devices. Now, are there any questions so far? Anything? Sure. Mm-hmm. Which part would you like me to explain? So, now, So basically, in the case of density of states, we are interested in the available energy states per given energy. Okay? So at 0 Kelvin, we know that all of these states will be filled. Okay? So this is the 0 Kelvin case. Now the idea is this. Well, we will not be working at 0 Kelvin always. We will be interested in temperatures that are greater than 0. So we introduced a quantum statistics called Fermi-Dirac statistics. Okay? And this statistical behavior tells us what would be the filling of electrons with respect to temperature. So the distribution function was something like this. So we have the energy of the given state and its difference from the Fermi level divided by, if you like, the average energy of the system plus 1. And if you plot this distribution, it will look like something like this at 0 Kelvin. So it's like a step function. The probability below the Fermi level is 1 because electrons or whatever particles, quantum particles, fermions you have will start filling up the lowest energy state all the way up. And you'll find no particles above the Fermi level. But as you increase the temperature, this is what you will get. The distribution now, as you increase the temperature, some of the electrons statistically will have enough energy to fill up these higher energy levels. Okay? So if we go back to this density of states picture, now ignore this shaded part, we still have available states at higher energies. So to figure out what the filling would look like, I have to basically take the statistical distribution into the account. So to figure out the filling, what I need to do is I need to integrate the density of states with the distribution over the energy values. And what we end up getting is something like this. So now some of the electrons at these states will be transferred to here, to higher energies. So the distribution is now more like this. So this is about basically how you fill up the available energy states in your system. At 0 Kelvin, we start filling up our system from the ground level up. And for semiconductors, we had this rule for insulators. If there is an even number of electrons in the valence, then the material turns out to be an insulator or a semiconductor, depending on the gap. And when you start filling up the states, this Fermi level can reside anywhere. It can be within the gap, it can be within the conduction band, it can be within the valence band. Well, then it won't be a valence band anymore, but you got the idea. It can be positioned anywhere depending on basically the number of electrons you have in your system. So the distribution, the filling, will start from bottom up, and for instance, you fill up till here. Since your Fermi level is within the gap region, you cannot have any electrons here. As you increase the temperature, because now you have this distribution, you can take some of the electrons from here to here. There's probability of finding electrons, and this is a more proper way of looking at this thing. So this was the case for our intrinsic conductivity of semiconducting materials. Is it now more clear? Okay. Any other questions? Yes, please.
Does the B-type atom also, make four
Mm-hmm. Yeah.
And the extra electron
Mm-hmm.
will come from silicium or?
Yeah. So now we have, if you consider this picture, we have, let me draw it this way. Let me draw these silicon atoms as well. What we are looking at here is a dynamic picture, okay? So let's say we have this. Of course, drawing a single impurity doesn't make much sense because it's really difficult to have a single impurity. But imagine we have lots of impurities within each other. Actually, a meaningful impurities are on the order of 10 to the 12 impurities per cubic centimeter. Okay, so we have lots of impurities in a crystal, and what will happen is, let's say this guy is missing a bond, but now there's an extra electron from the neighboring silicon, and there's also another boron, let's say here, and there's an extra missing electron here. So this electron can be used for making bond here. So effectively, you have an absence of electron here. So, but then this electron can come here and fill this hole. So you won't have that absence of electron. But then you created an absence of electron here. So again, it's like this hole moving in a certain direction. Of course, this is going to be an averaged effect. This absence of electron will be moving around. So we picture it as hole moving around. Okay? So in essence, this absence is always changing place. So to answer your question more directly, the answer is both yes and no. Some of them make 4 bonds, some of them make less bonds. So the overall effect is that a hole moving within the crystal. Okay. Anything else? All right. So now there's one thing we can do to actually calculate the energy of this system, the ground state energy of this system. And I'll just write down the answer. If you remember, the energy levels for the hydrogen atom are minus 13.6 eV. This is the ground state. And then they'll go with 1 over n squared. So for each state, this is the minus sign comes because this is with respect to the vacuum level, there's 0 electron volts. So as you go from the ground state to higher excited states, this energy will decrease. And this number actually comes from something like this. We have 4 pi epsilon 0 h bar squared. Okay. So these are all constants of nature: electrons charge, electrons mass, pi, epsilon 0, h bar So these are all constants. You can reach to this conclusion from Bohr's model or by directly solving the Schrödinger's equation. They give both the same answer. Now, in the case of an environment like this, of course you will see that now we are not dealing with an electron that's completely free. It's within this crystal, so there is an effective mass. So what we need to do is define an effective mass here. Okay, and then this epsilon zero, this is the dielectric permittivity of free space, but we are not in a free space now, thus we need to have the dielectric medium. We have to take that dielectric medium into the account. H bar doesn't change, pi doesn't change, electron's charge doesn't change. So with these modified terms, we can model this hydrogen-like atom. And indeed, if you do this calculation for silicon, and if you use, let's see, I'm trying to figure out what values I used for silicon, but anyways, I couldn't find it. If you do it for silicon, it turns out that the energy of this guy is about 20 millielectron volts. And the measured value, this is from calculation, is 29.8 millielectron volts. It's not a good agreement, but at least we are in the same ballpark. So the reason is this assumption is extremely simple. This effective mass and the dielectric medium actually in a real silicon crystal is much more complicated, but still it agrees to a certain extent. Then there's another quantity that's related to the hydrogen atom, which is called the Bohr radius, which is normally 1.53 angstroms. Angstrom is 10 to the minus 10 meters. Okay, and Bohr radius for such an impurity turns out that it is, let me see if I have the number. Well, I don't. So basically this is something you get m star over the mass of electron angstroms. And let me see if I must have written it somewhere. Well, I haven't, unfortunately. So, but this is the value you get. Now, but as you can see, it's going to be much larger than the Bohr radius, because the effective masses are typically much smaller than the free mass of the electron. So what you end up with is a much larger radius that can range up to a few nanometers within the crystal. Now, these impurities, if you put enough dopants within the crystal, these, for instance, the doping level is so high that this electron can, or the wave function of the electron can overlap with the wave function of the electron from the next impurity. Then you can create bands of new energy bands within the forbidden gap. But we are not going to look into such cases. We will be focusing ourselves into moderately doped cases. Okay. Now, looking get rid of this part. Now the question is this. We have seen semiconductors and we discussed metals. And now we should look into making some functional devices out of these. So far we have seen semiconductors, and we also looked at metals. And in the case of semiconductors now, we had the intrinsic case, we have n-doped case where we have excess electrons, and we have p-doped case where we have excess holes in the system. So, can I use these guys together to make some functional electronic devices? And the answer is obviously yes. Now, the first thing that I'd like to do is take a piece of semiconductor and really zoom into the surface of this semiconductor. Because eventually that's where we need to be focusing at. Now, let's take a one-dimensional semiconductor, okay, for a case of simplicity. Let me draw a few more ion cores. Now, what was our basic initial assumption when we calculated the energy bands and so on? What did we use? Well, that's one, but what else? When solving the Schrödinger's equation for a periodic lattice like this, what did we use? Yes, it has a name. Yes, Bloch's equation, right? Bloch's theorem. So the idea here is that we have this periodic arrangement of the potentials, and we even simplified this to an extent where we had potential wells like this, and this was the Koenig-Penny model. Okay? And the idea here is that if you take a wave function at any position, it must be a function that is, it must be a function of a periodic function, okay? It can be written like this. So this was the Bloch's theorem, because the idea here is that the potential was basically, let me write this, V, periodic, with certain periodicity, okay? And the solutions to the wave function had to follow the periodicity, and thus it simplified our solutions. And if you remember, we ended up with energy gaps opening because of this periodicity statement. And in essence, at very low levels, this stems from the interference of waves from one well to the other. Thus, certain waves interfere distractively, some others interfere constructively. So energies with forbidden regions open and allowed regions open. So that was the idea. But I'd like to bring your attention to this periodicity. Now, if I go to the edge, what will happen to this periodicity condition? Yes. So we break the translational symmetry of the system. No longer when you're here or here, you can no longer say that this potential is periodic. So this requires a special treatment of the problem. You cannot just use the Bloch's theorem and assume that there will be periodic wave functions. Now, the actual treatment is rather a difficult one, but I would like to write down some of the results that can be obtained by solving the relevant equations. So, I don't have them here. Doesn't matter. Now, I'm not going to again go into the details of the solution. There is this famous paper by Shockley. It's a 1939 paper. It's a very early paper. So this is only a few years after real use of quantum mechanics. So he solved this problem for 8 atoms. Okay, so he took a chain of 8 atoms and then solved the equations, relevant equations, to figure out how the wave function would like and how the energy states would look like. And for the probability density, this is what you get, sort of. So at the very edge, of course, I'm considering an 8-atom chain. So unlike this case, here we are only bounded by one side, but here you're bounded by 2 sides. But this probability density tells us something very significant. It says, for such a small chain of atoms, the electrons would be localized at the edges. So they'll actually travel to the edges, and the probability of finding an electron is much more significant, much more larger at the edges compared to the center. Which means I'm going to draw. Now, of course, we are assuming certain things here. Now, let me draw these atoms. Of course, we are saying that I have a lattice constant of A, and this solution now can be changed. Let's say this is the lattice constant, and this is the energy. It's a rather difficult to draw diagram, but I'll try my best. First thing is, for sufficiently large A values, which means if your atoms are separated from each other by great distances, the wave functions will not overlap, which means that the electrons will only be localized at the positions of the atoms. So there will be no band formation. Energies will be discrete. So you'll start from E1 and then it will go up. There will be discrete energy levels for each atom. Now, as you bring them closer at a certain critical value, these energies will start branching out because of the overlapping of the wave functions. And I don't know how to draw this, but what happens is basically this. Some of the branches will branch out like this. Let's say this is some other A value. So these branches will be like this. And then there will be another branch like this. But then I'm trying my best to replicate this, but it's rather difficult. So these branches and these, and these are the bands that we know. Okay, it's the regular energy bands that can be formed in a continuous change of atoms that has periodic boundary conditions. But these two states, that one comes from an upper energy level, one comes from a lower energy level, these are the surface states. So, what does that mean in human language? If you look at the edge of a semiconductor, this is the conduction band, this is the valence band, and this is the edge. Now, this is my real space axis, x, and this is the energy. If you look at the edge, this is what you will see. For a certain length, since the electrons can localize there and can create extra energy levels, you will form a band of available energies, okay? And these are called the edge states, okay? And they are only found at the edge of the crystals. And now, since my Fermi level for an intrinsic semiconductor goes through these edge states, I'll have some electrons here as well. Now that's important because in many cases for the mesoscopic physics, we'll be dealing with the very ends of crystals, surfaces of crystals. So from the rest, from the bulk, this is how surface differs. Of course, this is, again, you have to take this always with the perspective of the single electron model. We have certain assumptions still in process of these calculations. We are assuming that we are ignoring all the interactions of electrons with the rest of the systems. But there are many other things that we have to consider. For instance, if you take a silicon surface in ambient, it is a mass. It reacts with oxygen very rapidly. Then you'll have these silicon atoms it binds to an oxygen. Silicon atoms that binds to, I don't know, oxygen and hydrogen. And other defects, charged impurities. So a real surface is not a pleasant system like this. You can create really nice surfaces. That's another story. But an actual surface of, for instance, a silicon is a mess. It's chemically very active. It's chemically very unstable. There are lots of dangling bonds that it can react with, lots of other stuff. But in our simplified model, still this is a simplified model, we can see that there will be edge states. And actually we can create such nice surfaces with the modern machinery we have. For instance, you can evaporate atoms of certain type layer by layer to create a very nicely crafted surface. So this is one way to look at these edge states, which lies within the Fermi level. Of course, things will get very interesting when we introduce doping here, which I'll not do now. I'll introduce this later on when we'll start really using these ideas. Now, yes?
I didn't get this one. Why electrons are localized at the edge and
well, let me see. I don't know how to explain that without actually solving the equations. I'm not sure how to answer your question.
And impurity might change, I think, the existing legislative system.
Well, it will affect, because now my Fermi level will be at a different position. And here we have an assumption, and I'll come to that point, but we assume that the system is neutral in terms of charges. When you shift the Fermi level beyond its original level, now you have to account for that shifting by displacing some charges from certain places to certain places. So that impurity will result in bending of the bands. But again, I'll come back to that point. But to your initial question, I don't know how to give a physical insight of how to interpret localization of electrons at the edges. I just.
I have done this numerically once, like, okay, you can see inside that it's
Mhm.
really meant to localize at the edge.
Mhm.
But I mean, I also was looking once for a physical concept why this happens.
Perhaps we can. Let me see. I mean, now this is the vacuum level, and then you'll have this sort of periodic potential. So I just need to check how the this. Actually, I have the plot of the potential on my online lectures. Oh, we have it here as well, I guess. I would assume.
Is there any magnetic field or here or?
No, nothing. Just the surface. So I think, I mean, here's how the potential looks like. So it's periodic within the crystal, and then at the very end, it is partially terminated, which means the energies there are going to be lower. So the probabilities of finding electrons there has to be higher. But still, I never questioned it, to be honest. I said, okay, this is the solution, and accepted it. So thanks for asking that. But probably it has something to do with how the potential energy is terminated at the edges of this chain.
Maybe that here is broken, something happens.
Mhm. Okay, so let's give a 10-minute break, and then we'll continue with more surfaces. I can take the homeworks, by the way. Now that was the surface of a bare semiconductor. Now, what I'd like to do is take a piece of metal and take a piece of semiconductor and bring them together, attach them to each other. So, let me find the relevant part first. Now, as for the metals, if you remember, now the band diagram would look something like this. So, this is my Fermi level, and it's below that Fermi level is completely filled. And also for now, let me define a zero energy value. Okay, so this is the vacuum level. If you go far enough from the surface of a metal or from the metal itself, then the energy here, I assume, is that it's zero. And for the semiconductor, this is what I have. Let's deal with an intrinsic semiconductor. This is my Fermi level. This is my conduction band. And this is my valence band. Now the question is, what will happen to these bands when I bring the metal and semiconductor closer to each other and eventually touch to each other? Now, there are a few concepts that I have to introduce before doing a formal treatment. Now, the first thing is regarding this energy difference. So, this energy difference defines the energy required to take an electron from the surface of a metal and bring it sufficiently far away to the vacuum level. So obviously this is going to take some energy because these electrons are actually binded to this metal, just like an hydrogen atom. So this guy is called the work function. Okay, so it's defined as the energy required to take one electron at the Fermi level or at the band edge of a metal to the vacuum level. That's important quantity because it sort of determines where the Fermi level lies with respect to the vacuum level. As you will see, this will be extremely important in defining relation of a metal to a semiconductor. Now, for the case of semiconductors, it's rather silly to define a work function because my Fermi level lies within the energy gap. So, by the definition of the work function, it's energy required to take an electron from Fermi level to the vacuum level. But here, it's an ill-defined quantity. Rather, what we introduce is another concept. I don't know what people use to denote that. Okay, guy, and this guy called the electron affinity. So, in a way, it's the energy required to take one electron from the edge of the conduction band to the vacuum level. So it determines basically where, in a sense, where the Fermi level is located with respect to the vacuum level. Now, there can be very interesting cases. For instance, if the work function of a metal is much greater than the electron affinity of a semiconductor, then you can have, I don't know, something like this even. That's, I mean, it may seem crazy. So this is the Fermi level, and then this is my metal, so this is the Fermi level of my metal. So there's a huge misalignment, and the Fermi level of the metal coincides with the valence band of the semiconductor. So that's one extreme case. It can be the other way around. And as we'll see in a minute, this alignment will determine how this connection will behave electrically. So we'll come back to this. Now, one interesting thing is, let's go back to this case. When you start bringing these two surfaces together, something strange happens. We start forming states called metal-induced gap states. Now, what happens is basically this. Let me draw this conduction band of the metal, and then this is the conduction band of the semiconductor, and this is the valence band. And at the very surface, this is induced gap states. Okay, we typically denote it with IGS. Now the idea is this. When this metal is sufficiently close to the semiconductor, by sufficiently close, we're talking about less than a nanometer or within the range of a nanometer. What happens is that at the edge, now I deleted that, but let's again take a look at this one-dimensional chain and consider the wave function of an electron at the outermost atom. It will leak towards the out of the material, okay? So this is the wave function, tail of the wave function for this chain of atoms. Now when you bring this metal close enough, this wave function will leak into the metal, and the electrons within the metal, now it can, you can form this continuous wave function in a way, and this is a very crude way of speaking, but now this electron can jump, or it's not like a real jumping, it's really, there's a finite probability of finding the electron here at this position. It creates new energy states. Okay, this sufficiently bringing these two closer will result in this wave function to be continuously travel into the metal. So there's a probability of finding this electron within the metal, which introduces new energy states. So what you end up with is this continuous band that's at the very edge of the semiconductor, and these states will be filled as well when you make a connection with a metal. Now let's do that. I'm gonna get some help from the drawings in this book. Now what happens is this. In this case, this is my metal, okay? And now it's in contact with the semiconductor, okay? So this is the valence band of the semiconductor, conduction band. This is my metal, and now I have these induced gap states. So first, the electrons here have lower energy compared to the metal. So some of the electrons upon contact will fill this part because we are trying to minimize the energy of the state. Electrons will seek for the lower energy states and fill them up. So what will happen is now I'll have some electrons that fills this induced gap states. But now I have excess electrons here. And these excess electrons will modify the bands in such a way that these bands, energy bands, will bend like this. Okay? Because of the excess charges that are here. So in the case of neutrality, there's no bending. But now, since I have these excess charges, there will be bending of the bands. Now, this is an intermediate case, and it's not too stable. The next thing that will happen is basically this. So again, let me skip this energy thing. So this is my Fermi level for the metal, and then let me see. This now my Fermi level is here, okay? So I cannot have Fermi level differences throughout a single body. So this Fermi level will be reduced by moving more electrons into the from the semiconductor to metal. So what will happen is that this band will bend even further, so that the Fermi level, this is rather exaggerated, will be equal with the metal itself. So in many cases, by many I mean probably like 99.9% of the cases, this depth is so shallow, it's less than a nanometer, it hardly matters. Actually, to be able to observe this, you have to construct this structure very carefully. So one example is that they have, for instance, aluminum layers, a few atoms of aluminum, and on top of that, they grow indium arsenide. And in such systems, they can show opening of these induced gap states within the first few layers by using scanning tunneling microscopy. But in many cases, it doesn't extend beyond a few atoms. I'm introducing this because we'll see a point where it will become useful. But for now, we can safely say this. When I make a contact with a metal, the bands will bend in such a way, it may bend actually in such a way. Okay, so I basically ignore this induced gap states when I draw band diagrams for these metal semiconductor junctions. Any questions?
I don't understand the formation of induced gap states.
Okay, so again, now we have the semiconductor, okay? And if you look carefully, I'm again going back to one dimensions, there are only a few atoms at the edge and they break the periodicity. So if you look at the wave function of the electrons here, you'll see that the probability actually leaks out a little bit. Let's say this is the probability density. And you will find that there's a finite probability of finding an electron within a fraction of a nanometer out of the surface of this material, or a few nanometers. Okay? So let's say this is 1 nanometer away from the surface of the material. Now what I do is I bring a metal here sufficiently close so that this electron now can, let's say, tunnel into the material, into the metal. So now this tunneling results, previously we didn't have such thing, but now we have it. It results in formation of new energy states. Okay? We modify the wave functions, thus we modify the energy distribution of the system. So at the very edge, at the very surface of the material, we modify the available energy levels. So no longer we have this band gap, but rather we have energy states that are available. Okay? And now what I try to show you here is what happens if I make a contact. Upon contact, what will happen is now I can transfer electrons to the energy states that are available here. And the way I have drawn it is that the electrons that I have here have higher energy compared to the electrons here, which means the electrons will want to move into these states. But upon doing, I transferred lots of charges to the semiconductor, at least the surface. There will be a band bending. But now, another problem, I'm doing this step by step, my Fermi level for the bulk of the crystal is higher. Well, that's not how I draw it, but suppose that it's higher than this Fermi level here. So throughout the sample, I have to have a uniform Fermi level, because in a way, Fermi level determines the energy of the electrons at the edge of my Fermi sphere. So you cannot have discontinuities in the energies of electrons, because this electron now knows that there is an energy state with lower energy, so it will travel through there. So there will be, to be able to balance out these two sides, the bulk of the semiconductor and the metal, I have to transfer some charges from here to there. Thus, in the end, what I end up with is a configuration like this. I have same Fermi level throughout my sample, including metal and the semiconductor. And as a result, a certain length at the interface, the energies will be bent. Okay? So this is called band bending. Okay? So this is shifting the energies with respect to the vacuum level, so that you have same energy throughout the crystal. Hope that is clear. Well, this, yes. That's a much deeper story than that. Okay. Now let's give a 5-minute quiz break, and then we'll continue with bringing metals and semiconductors together. Okay. Let's finish. Thanks. Okay, now this is rather might seem a little abstract to some of you guys. So let's try something slightly different and look at it in a different way. Now, rather than a metal and a semiconductor, let's take an n-doped semiconductor and contact it with a p-doped semiconductor. So on this side, this is what I'm going to have. This is my conduction band. This is my valence band. This is the Fermi level. And on the other side, this is what I'm going to have. So what will happen when I bring these two together and make a junction? Well, when you bring them sufficiently close together, there will be induced gap states formation. But I'm going to skip that part as we're not going to use it. So this time the induced gap state formation is rather different because there will be two discrete gap formation, but it's not really, it doesn't matter too much. Now let's try to look at what will happen in a more physical way rather than this abstract way. Okay. Now at the very surface of p-doped, and this is n-doped, I have these holes, okay? And also I have these holes at the bulk of the crystal. And here I have excess electrons. Okay, so these are electrons and these are holes. Now what will happen at this interface? I have a positively charged particle and a negatively charged particle. Yes. What's the name of this process? No, I'm asking for a positively charged particle attracts a negatively charged particle. Much more simpler. Physics 102. No? No? What is the name of the force between Coulomb force? Okay, there will be a Coulomb attraction between holes and electrons, okay? So they'll attract each other. Physics 102. Now, let me start combining electrons with holes, because remember, holes are not real particles. They are absence of electrons. When you fill it with an electron, the system will be satisfied. It will be filled. So I'll remove one electron from here and remove one hole from the other side. They're recombined. Everyone is satisfied, or perhaps not, because for every electron that will leave here, and for every hole that will leave here, there will be an unscreened impurity left behind. Okay? So they'll recombine and recombine. So eventually what I'm going to end up with is a region of space with lots of ion cores, with positively charged ion cores left behind here, and lots of negatively charged ion cores left on the other side. So this will create an internal electric field. right? I have positively charged particles and negatively charged particles. They are fixed in space. They cannot move, unlike electrons and holes. So I'll end up with an internal electric field. Now, what does that mean? I mean, why doesn't this annihilation of electrons and holes continue for the bulk of the crystal? Because the reason is this. At some point, this electric field will become sufficiently strong that the attraction by this negatively charged particles will not be as strong as the repulsion by the positively charged particles here. So these holes cannot pass through this built-in electric field. Likewise, the electrons, they'll be attracted to here, but the electric field from here, this negatively charged ions, will not allow electrons to pass to the other side. So at some point, at some critical length, okay, some length, this process will stop. So you will have electrons on the other side and holes on the other side, and a zone where you have no carriers at all, which is called the depletion zone. So you depleted all the electrons and holes by combining them together, because their energies are different. Okay? Now, this is one way to look at it, or another way to look at it, just like what I have done over there, is this. Now, throughout my crystal, I need my Fermi levels to be equal, okay, so that they'll have the same energies. So what I need to do is I need to shift this guy up in such a way that they'll have the same Fermi levels. Now, of course, I mean, this is almost an arbitrary move, because to be able to do that, what I need to do first is I need to start transferring charges from one another. Okay? So what I need to do is basically this. Some electrons will be transferred here, and some holes will be transferred here. So this band will start bending upwards, okay, and will be combined with this. So this is my continuous Fermi level. Oops. Okay, and this band will curve upwards, so it will be combined with the other. And this region here, now, is going to make more sense. This is my P-type region, and this is my N-type region. And remember, there is a built-in electric field. And if you think in terms of simple electrostatics, of course, this is not completely true, but electric field times certain length will give you the potential difference. Okay? So since I have my electric field pointing in that direction, I would expect a potential difference of some V between these states. Okay? So when I go from this side of the crystal with an electron, this is drawn for electrons, this electron will see a potential step. So it won't be able to overcome. So let's say I have my electron here. So the whole energies here are equal for each position. So I can take my electron effortlessly till this point, till the edge of the depletion zone. But now there's a potential difference of V that this electron has to overcome. So it cannot by itself, if I don't provide sufficient energy, overcome this potential barrier to be transferred here. Let's play the movie from the other side. I have an electron here. I send it this way. Here, there's a lower energy state. So it will happily travel to the lower energy state. You can do the same thing for holes, but you must remember that holes are positively charged. So the image that you see here has to be flipped upside down. So for a hole that comes here, actually, this is a potential barrier. Okay? So it cannot pass from this side to this side, but a hole that comes from the other side will be able to pass from here to here. So what is the name of this device? No, it's a diode. So if you try to plot, this is the voltage, this is the current. Of course, it's slightly more complicated than what I draw here. But for the forward biasing, which means I apply potential from here to here, my electrons will see no resistance at all. They'll see the regular resistance of the crystal. But for trying to send electrons from here to there will be a huge resistance. So, okay. And of course, at some point, there will be a breakdown. But it's a device that allows passage of current from one side while it prevents its passage to the other side. But don't focus on what this device is now. My aim here is to really make this connection between these rather abstract band diagrams to actual physical events taking place within the crystal. I hope that that's clear. So because of charge transfer, because of this imbalance between the energies of electrons on this side and this side, there will be a charge transfer from one side to the other. And that charge transfer results in built-in electric field creation, which in a way determines how the electronics of this junction will behave. And we can think about a similar story here. Again, we have electrons with higher energies on one side and material here as electrons with lower energy. So I start transferring some of the electrons, which in a result ends up being at the interface accumulating charges, which results in a potential difference between the bulk and this region. So I end up bending the bands in such a way that when an electron comes from this part, it will encounter an obstacle here. So if I try to send an electron from this side, now it needs to overcome this potential barrier before it can really make it to the metal. And same applies sending an electron backwards. So now I don't have too much time left, but obviously, as you can see, this is a very simplified picture that I've drawn here, because I adjusted bands to be exactly the same and I shifted the Fermi levels in a way that I wanted. But in reality, these PN junctions can be formed by vastly different combinations of materials. You can have a large gap material and a narrow gap material, or the electron affinity of one semiconductor can be vastly different than the electron affinity of another semiconductor. Even there are cases where you can make, completely staggered formations. So depending on how the electron affinity, or in this case, the work function and the electron affinity are aligned with respect to each other, conduction properties of the materials can be very different. You can have a diodic transfer, like it can act as a diode. You can have a junction between a metal and a semiconductor that can act as a diode, as well as you can have such a junction where you have a linear IB. So no barrier formation, as in this case. There will be no barriers. The electron can easily get transferred from metal to the semiconductor. So you end up with an ohmic contact where you can define a global resistance for any values of voltage. Okay? And as we'll see in the next lecture, I'm going to finish in 2 minutes. This guy is called a Schottky barrier. Okay, so this barrier is named after this guy. I think there are 2 T's, right? Schottky. It's called Schottky barrier, and the contact, as we'll see in the metals, we can have Schottky type contact. So again, we are going to discuss these types of contacts in detail in the coming lecture. And also in the coming lecture, we'll finish this introductory concepts. We are pretty much done with the electronic states of semiconductors and metals and how sort of they behave at the surface. And I'll introduce transistors because as we'll see, they're very important in many of the mesoscopic phenomena. So how you can construct a field effect transistor and how they behave and their band diagrams. And then we'll move on to introduction of some mesoscopic parameters that we have seen at the very beginning of the class, at the very beginning of the course. And we'll look at now these parameters in more details and how they are related, and then we'll start talking about electronic transport through these structures, and we'll try to create some models. So, any questions?
So we have only 2 types of counters, ohmic and Schottky.
Yes.
In the case of semiconductors.
Well, it doesn't have to be, well, of course, you cannot make Schottky contacts among 2 metals. The reason is simply, even if you have different work functions for different metals, as soon as you bring them together, some of the electrons will be transferred here, and there will be an equilibrium. You cannot create bending in metals. So, to be able to form a Schottky barrier, I guess you must have a semiconductor. At least one semiconductor. You can form a Schottky contact between metals and semiconductors, and this can become either a very big problem or it can be something desired. So it depends. But then for many applications, especially for making good contacts to certain materials is critical for measuring their intrinsic properties, then you need ohmic contacts. For instance, for our 2D materials, we rarely want diodes at the interfaces, but it's very difficult to get non-ohmic contacts to the 2D semiconductors. Okay.